Good morning to all. So today we'll start microwave engineering subject. So this is for EC BTech fourth year first semester, regular and ADP. So coming to syllabus, actually we are studying in this course starting with microwave transmission lines. So already the basic prerequisite subjects to understand this microwave engineering is electromagnetic theory and transmission lines plus electronic devices and circuits. So first two chapters for first 2 units we require the basic fundamentals of transmission lines. So whenever we are starting to discuss about microwave devices, so we need some fundamentals of EDC like MOSFET, JFET, and the basic transistor uh, properties. So coming to first chapter, we are going to be discuss micro transmission lines. That means we are going to we already studied transmission lines in the EMTL. Now we are extending the transmission lines into uh, high frequencies. There in EMTL we discussed for the low frequency RF frequencies. Now here we are going to be extend towards the high frequency applications. So what happens whenever we are changing from low frequency to high frequencies? What are the difficulties we can face? What are the advantages? What are the disadvantages? We are going to be discussed in this first chapter. So first we started with introduction, followed by microwave spectrum. So what is microwave and what are the frequencies involved? What are the advantages, disadvantages? Where we are using this microwave frequencies. Later we discuss microwave bands. We have different types of bands. So we'll discuss all bands and applications. So after discussing these applications, we'll enter into the waveguides. Actually, this is the extension here we are using for high frequency applications. We are using the waveguides. So instead of starting rectangular waveguide, I will start with parallel plane waveguides because that will give command to understand the rectangular waveguide. So I will give this brief introduction to the parallel plane. What is the difference between the parallel plane waveguides and rectangular waveguides? So then after we'll discuss thoroughly about the rectangular waveguide. So basically we have three different types of waveguide, but as per our syllabus, we are going to discuss rectangular waveguide, solution of wave equations in a rectangular coordinates, TE and TA mode analysis, expressions for the fields, characteristic equation, cutoff frequency, filter characteristics, dominant and degenerate modes. So these are the very important because whenever we are what frequencies we can use in a microwave devices that will be decided by these dominant and degenerated modes. So we'll discuss thoroughly about the modes, and also we discuss sketches of TE and TE mode fields in the cross-sectional mode characteristics like phase velocity and group velocity, wavelength and impedance relations, power transmissions, and impassability of TEM mode. This is very important because TE, TM, TEM modes will be exist in transmission lines, normal transmission, RF transmission line. But coming to microwave transmission line, microwave waveguides, TEM mode is not possible. That we will discuss, will derive with expression wise, the concept, derivation, and why it is not possible. We'll discuss. Similarly, we'll just do some problems. So later we'll discuss microstrip lines, basic introduction and dielectric concept. After completion of this first chapter, we'll start with cavity resonators, right? Waveguide components and applications. So after understanding the waveguide, rectangular waveguides, where we are using these waveguides, because after learning a lot of we know waveguides are used in high frequency applications. So where we are using high frequency devices, so that's cavity resonators. So we are generating the frequencies, high frequencies, resonating the frequencies in the cavities. So first we discuss introduction about what is cavity and what type of cavity resonators we have. Then we'll discuss rectangular cavity because the first chapter we are discussing only rectangular waveguides. So here we are also discuss only rectangular cavities. its dominant modes and resonant frequencies, Q factor. So a resonator will functionality of the resonator will be decided by its Q factor, and also we discuss coupling coefficient and we'll do some problem. So after that, waveguide components, because we know waveguide in EDC we studied components like active components and passive components. If you have transistor or MOSFET or diode, you can't use a single alone the transistor diode. You need some uh, components to be attached or to be connected to get a circuit, to get an application like resistor, capacitor, inductor. Whenever we are adding that passive components to your BJT or FET, definitely it will sense. It is a sense. Similarly, here we have the waveguide components and applications. So starting with coupling mechanism, probe, loop, aperture types, we'll discuss three different types and discontinuous, mature loads, waveguide attenuators. So we'll start with microwave bench. So in that bench, what are the components involved? What are the active components and what are the passive components? So, and we'll discuss what are the purpose, what are the functionality of every component. Plus, we'll start with, we'll discuss waveguide attenuators, waveguide phase shifters, and magic tees, directional couplers. These all are the waveguide components. These components will be used in microwave, in the microwave bench. So to establish a microwave bench, we require active sources as well as passive sources. Active sources, how we are going to be generated the frequencies by using the tubes. We have the M-type and O-type tube that we'll discuss later in the upcoming sections. And also we discuss ferrite component, ferrite devices. By using the ferrite material, we are going to be discuss the three different types of material: variator, circulator, and isolator. Going to third chapter, in the third chapter, after we are discussing microwave tubes. So first we are we'll start with what are the limitations of conventional tubes, because we have the before microwave tubes we know the very basic conventional tubes like the vacuum tubes. What are the functionality? What is the functionality and what are the disadvantages over high frequencies? What happens if you apply the very high frequency to the vacuum tube? So after discussion of that entire scenario, we'll start with microwave tubes. So limitations and the losses at a conventional tube at microwave frequencies. Microwave tubes, the classification, we have two different types of tubes, O and N type. So in the O type, klystron, helix, TWT, in the klystron, two cavity and a reflex klystron. After helix TWT, we discuss N-type tubes. Here, cross-field effects, cross-field type tubes. So we'll discuss magnetron. So we know the very best example of the magnetron. Generally, we are using in our daily life, in the home appliances, like microwave oven. In microwave oven, we are using magnetron. So after that, we'll discuss on microwave solid-state devices. What are the solid-state devices we have in the EDC? Like BJT, MOSFET, JFET. Similarly, here and thyristors we have. So here also we have gun diode, avalanche transistor devices, RWH theory, MESFET. And for here, as per our syllabus, we don't have a MESFET, but similar to MOSFET, we have MESFET here. Similar to BJT, here also we have high frequency BJT. Similar to diode, here we have GaN diode. So we'll discuss solid state devices for microwave. Lastly, in the fifth chapter, so after establishing the circuit or the network, we need to analyze, because how can we estimate the performance of the network or circuit? So we need to apply some analysis. So in the basic elements like resistor, inductor, capacitor, we are used this BJT and all active sources. We use network analysis. That means we are going to be estimated by two-port networks, parameters like Z parameters, H parameters, G parameters. We have different parameters, but that parameters will not work out at the high frequency. That parameters, then that analysis is suitable only for low frequency applications. So for higher frequency applications, we are going to be use scattering matrix S parameters. So we'll start with understanding the significance of S matrix. formulation and properties, and the calculations for two-port junction, three-port junction, or four-port junction. So we'll start with two-port junctions. Like already in the time of second chapter, we'll discuss the passive components, E plane and H plane T, magic T, circulator, isolator. That whatever the components we discuss, we'll analyze by using S parameter, and also we'll discuss some problems here. Finally, microwave measurement, because here you are generating some power and you are using some power, right? So that power, that energy is some, not only power, it may be attenuation, or it may be frequency, it may be VSWR. So we are going to be measure these different types of parameters. So we'll start with description of microwave bench. Already with because to understand the my component, will start this description of my equipment as the first, then different blocks of the features, errors, precautions, power measurements like bolometer, measurement of attenuation, measurement of frequency, measurement of VSWR, whether it's a low VSWR or high VSWR, cavity, and impedance measurement. So what are the textbooks you have to follow? So the thing is, we have one book, Microwave Devices Circuit, Samuel Y. Liavo, is a one book, and second book, as syllabus mentioned, Herbert Jerry, and also you may go with the reference Fundamentals of Microwave Engineering, Colin, as well as Fozar, Microwave Engineering by David A. Fozar. These are the books you may follow. Coming to introduction. So why have to study this microwave engineering first? So basically, this microwaves was introduced at the time of Second World War to develop the radar system. So in that microwaves having basically the name itself saying microwave. So it has a micro length wavelength or micro wavelength. So it's not the wavelength about 10 power of -6, but the micro will means that sense that little or low wavelength. So generally these microwave frequencies have ranged from 300 megahertz to 300 gigahertz. So if you calculate with formula F is equal to C by lambda, 3 into 10 power of 8 by 1 meter, you will get 300 megahertz, and it's up to 1 mm, you will get 300 gigahertz. So if you see here, the regions, generally microwave region 300 megahertz to 300 gigahertz, 1 meter to 1 mm, millimeter wave, and infrared. We have different frequency range and one wavelengths. And microwaves are short waves because of a higher frequency, lesser wavelength is short waves. And because of the feature of short wavelength, these waves will not replicated by ionosphere. Whenever you are transmitting these waves towards the space, the signal will not be reflected back. It will be penetrated into the ionosphere. It will not. These waves will not affected by ionosphere. But whenever you are transmitting the RF waves, radio frequency waves, definitely whenever the RF waves enter into RF waves, the nature is longer waves. So whenever the longer wave enter into the ionosphere, it will be reflect back to Earth, and we may identify the signal will be reflected back towards the Earth. Coming to electromagnetic spectrum, we know it's the spectrum non-ionizing and ionizing. So 0 to 300 hertz. We have different wide long waves to short waves. So the short waves will be penetrated into the ionization, and non-ionization having the longer waves. So here, this is the microwave. Where we have the band, and beyond the microwave, we have the infrared, visible, ultraviolet. So if you observe once again this graph, so long wave radio starts from 3 10 power of 3 wavelength, that means 1 kilometer wavelength into 3 into 10 power of 5 range. So AM broadcast, shortwave radio, VHF TV, this region is a microwave. Above that, infrared, above that, visible light. Yeah. So frequency band designation. So if you see the frequency bands, this is a basic phenomenon we already studied. So 3 to 30 kilohertz is a very frequency. Generally, we are using navigation and sonars. 3 to 300 low frequencies, radio beacons, and medium frequency 300 to 3000 gigahertz. Generally, we are using for the AM broadcast because the AM broadcast range from 550 to 1650 kilohertz. In this frequency band, we are using AM 3 to 30 megahertz high frequency. So we are using telephony, telegraph, and mail, shortwave international broadcasting, and 30 to 300 megahertz, very high frequency. This is a famous band because our radio operating in 88 to 108 megahertz. So FM broadcasting and air traffic control, ATC, and police mobile radio taxi cab. Coming to 300 to 3000 megahertz, so 300 megahertz to 3 gigahertz. So we are using UHF, ultra high frequency. Satellite communication will be involved. So this is one of the band of microwave frequency band. So UHF and SHF, EHF, these three are the microwave bands. So these three microwave bands, three UHF, SHF, and EHF, having lot of applications involved. Lot of applications are involved. We'll discuss that remaining applications in the lab. So if you observe this spectrum once again, we have this whatever the microwave band starting from generally we are considering from 1 gigahertz instead of 300 meg, 1 gigahertz to 1000 gigahertz or 300 gigahertz. But we have the basic bands, generally the general bands we are using in the general scenario. So 1 to 2 gigahertz assigned to one band, that discuss later. But here we need to understand from this plot, so lower frequency towards higher frequency. So whenever we are moving to the lower frequency to the higher frequency, throughput is lower, throughput is higher, antenna size. If the frequency is less, antenna size requirement is more. We know antenna size how it is related to frequency. As frequency is lesser, lambda is going to be increased. As lambda is going to be increased, length of the antenna is going to be increased. So as far if you are increasing the more frequency, antenna size is going to be reduced. And band spectrum. So here you can identify the spectrum of band is very narrow. So because of less frequency, you will get less bandwidth. Here more frequency, you will find out more bandwidth. Susceptible to rain fade. So these long waves comparatively uh, 1 gigahertz is the short wave, but comparatively 40 gigahertz to 1 gigahertz, it's a long wave. Susceptibility to rain fade is very less. Here, susceptibility to rain fade is more. Frequency bands, once again, LSC, X, KU, K band. So these are the millimeter wave bands, and these are the traditional microwave band, license except. So generally we are using this microwave band. So cellular also somehow we are using L band for cellular. So this is a microwave letter band designation by IEEE. L band 1 to 2 gigahertz. The basic application we are using satellite, low, low level satellites, navigation for GPS, cellular phones. The application cellular phones, we observed the cellular phone application like 800 megahertz by 1800 megahertz bands from 2G and 3G. And for 5G, 4G, it's 2.4 gigahertz. So in the 5G, it is going to be more than 5 gigahertz. So we are using these frequency bands for cellular applications. S band 2 to 4 gigahertz. Once again, we are using satellites and unlicensed band. So this unlicensed band, ISM band, we know 2.4 gigahertz. Mostly we are using for a Wi-Fi, Zigbee, Bluetooth, etc. We are using 2.4 gigahertz is the S band. Then C band 4 to 8 gigahertz, microwave relay and satellites, and X band 8 to 12 gigahertz for radar. So this C band 4 by 8, previously in the older days like 2004, 5, 6, we are using for satellite uplink frequencies 4 gigahertz and downlink is 6 gigahertz C. But nowadays we are using uplink frequencies 12 gigahertz, sorry, uplink is 14 gigahertz and the downlink is 12 gigahertz. So here, Ku band generally the satellite TV DTH will work out in 12 to 18 gigahertz. 14 by 12 uplink and downlink frequencies. Coming to K band, 18 to 26.5 gigahertz to microwave backhaul. Ka band 26 to 40 microwave backhaul. So generally we are considering up to Ka, and also we have more than Ka, Q, U, E, E, W, F, D up to 110 gigahertz. So here for WLAN and 802.11, we are going to use from V band 50 to 75 gigahertz. So what are the applications and frequencies? So just a quick preview. FM radio is 88 to 108 megahertz. CDMA is 824 to 890. GSM we have different bands. GPS 1.5 gigahertz. The 3G, 4G. So and we are using more applications in the satellite defense communication and also radars. So what are the advantages basically while using these microwave frequencies? The most first advantage is wide bandwidth. We are getting wider bandwidth. Why? What is the major advantage? What happens if you are getting a wide bandwidth? If you have less bandwidth, you can't transfer. You can find out less number of channels. You don't have such a capacity to transmit. If you have the wide bandwidth, definitely you will get you can create more number of channels. If more number of channels, you can transmit more information. The capacity is going to be increased. So the wide bandwidth, let's take an example. Let's assume that we wish to transmit a number of 4 kilohertz wide voice signals to a wireless link. Further, let's assume that we have two wireless systems to choose from, one operating at 50 megahertz and the second at 4 gigahertz, each with 10% of bandwidth around its center frequency. So here, sorry, one second, 50 megahertz. Yeah. So in theory, 50 megahertz system should carry how many number of channels? Operating frequency into bandwidth, percentage bandwidth by bandwidth per channel. So 0.05 gigahertz into 0.1, 10% bandwidth divided by 4 kilohertz, you are getting 1250 number of channels. If you increase your frequency 4 gigahertz into 0.1 by 4 kilohertz, then you will get 1 lakh channel. So see, if you change your frequency from 50 megahertz to 4 gigahertz, you can find about 400 times of channels, 1250 to 1 lakh channels. So we can get more number of channels, more capacity, so we can transmit more. There's a wide bandwidth. Second one, improved gain by directive properties. How the gain and directive properties will increase? So see, if you like consider any antenna as a parabolic antenna or helical antenna or helical antenna. So in the parabolic antenna, the directive gain is equal to 140 by d by lambda. So that d by lambda, lambda is the wavelength of the wavelength. So as frequency increases, wavelength is going to be decreased. As wavelength is decreased, what happens? Directive in the denominator, the lambda is there. So as it is decreased, the denominator is increased. So then automatically the directive gain is going to be improved. Less fading effect. So definitely higher frequencies does not have low frequencies will affect with more fading. So higher frequency because of microwave frequency, fading effect will be less, and low power requirements. So because of short waves, why it is low power consuming means, so microwave frequencies are short waves for that reason. So it requires less power requirement. And finally, it's obviously a reduction in antenna size. Already we discussed. So as the frequency increases, antenna size, aperture area, and antenna size is going to be reduced. What are the disadvantages in microwave frequency? The major disadvantage is it is line of sight propagation. So it will work out only for line of sight line of sight. So if it is the only line of sight, we need more. We need to place more number of repeaters in between source to destination, transmitter to receiver, and susceptible to electromagnetic interferences. So because of this microwave frequency will be interfered with electromagnetic waves because of TEM waves will be more susceptible to Wi-Fi electromagnetic signals like Wi-Fi or Bluetooth. Sensitivity to bad weather, yes, definitely we know the best example is whenever the cloudy or rainy is outside, your TV signals is going to be stopped. That means scrambled. Signal will be scrambled because of the signal coming from the space. It will be connected to the cloud. So because of the bad weather, the signal will be corrupted or scrambled. Costly. The microwave devices are more costly. So coming to applications, we have infinite, very wide applications. A few examples I discussed here. For communications, terrestrial, microwave links, cellular, WLAN. Already I discussed cellular, we are using a L band and somehow S band. So cellular application, we are using microwave links and wireless LANs. So, and also we are using in satellites like the best example is DTH. Radar. In radar also. In radar, the basic purpose of introducing these microwaves is using in radars, target detection and target tracking and detection, range finding. In the civilian, basically in radar, where we are using these radars, in civilian applications like ADC, air traffic control, ship traffic control, car traffic control, and remote sensing. Coming to in military areas, surveillance, navigation, weapon guidance, and electronic warfare. So coming not only this civilian and communication applications, we have biomedical applications, industrial and commercial applications, and home appliances. I already discussed the microwave oven with the basic application like microwave oven we are using in a home. These are microwave devices. Industrial and commercial heating for drying, cutting, process control, waste treatment, sensing and monitoring. And biomedical, we have different implantable devices here, hyperthermia, imaging, microscopy. So we have different type of applications. So let's start with the basic study. So history of electromagnetic waves. Because to understand the microwave frequencies, we need to understand the, because microwave frequencies are electromagnetic waves. We need to understand what are the electromagnetic waves it is start from. So to analyze or to understand the microwave frequencies, we need Maxwell equations. These four equations will be used for analysis of entire your microwave fields. So James. So coming to microwave engineering, radio communication, there is Chandra Bose, Alexander, Marconi invented radio. We have different scientists who is involved in yeah. Coming to microwave communication systems. So basically this microwave communication transmitter and receiver. So modulating signal, carrier signal, we are modulating and amplifying. But before transmitting through antenna, we are using impedance matching network to balance, to match the your microwave frequencies to your antenna and receiver side. So here receiver side RF amplifier, we are using mixer, local oscillator, IF and IF amplifiers, demodulator, and finally we are using the display device that speaker. So we know the output, if it is you are finding out the target range, so you need some displays. Or sometimes you are transmitting the voice signals, we require some speakers. In radar, generally we are using displays, A-type displays, O-type, P-type, B-type, C-type. We have different types of displays having different applications. So coming to microwave components and systems, so we have the passive micro components, P-line antenna, power divider, combiner, couplers, filters, attenuators. What is active? These are the passive. So active microwave components are amplifier, microwave amplifier, microwave accelerators, mixers, RF switch, phase shifter. So coming to microwave system, mobile phone, jammer, RFID, RF transmitters, radars, microwave equipment, energy harvesting, high power microwave systems. So these are the different microwave components, different applications. This is about introduction to microwave engineering. The next class, in the next lecture, we'll discuss introduction to waveguide, parallel plane difference between parallel plane waveguide and rectangular waveguide, and analysis of rectangular waveguide. Thank you.